Alright, so when it comes to modeling, it's very important that we take note of two things, symmetry and anti-symmetry. Okay, there's also what's called axisymmetry, but for now I just want to make sure we get down symmetry and anti-symmetry and really have a good understanding of what this is all about. For now I'm going to focus on symmetry. I'm going to spend about 10 minutes in this notebook on this topic, maybe just over 10 minutes, so that gives you about 15 minutes to play with the notebooks after the lectures, the videos are finished. So that's the spirit. Okay, so that you have some time as part of the class time to play with the notebooks, to make sure. There's also some breathing space for students that are behind. So I know that there are quite a number of students that are at the moment that have fallen behind. Okay, so I'm going to focus only on symmetry for today, and then tomorrow we're going to look at anti-symmetry. So that's really what we're going to be looking at. So bottom line is, fair models can be quite time-consuming, expensive to solve, and by spotting symmetry and anti-symmetry in the model, we can really reduce the computational cost. So what this boils down to is if instead of solving one large system, I can solve a much smaller system. So sometimes you can reduce the size of a system by half or by 1/4. Similarly, in a sort of 3D context, you can imagine I can do it in a half, I can do a quarter, I can even do 1/8 type of, when I apply some symmetries in some cases. Okay, so that's really why it's such an important thing. And it really becomes important, especially if it's not about a single analysis, but you want to do optimization, or you want to do calibrations, where you have to do multiple analysis to be able to do something sensible. So especially the optimization, I'd say, is quite important. So if you want to optimize the geometry of the structures, like a shape optimization problem, or the topology optimization, where we want to try and figure out what is optimal topology inside for the structure, so that there can be holes born or removed. That's the kind of stuff that is important. Okay, so these things are the things that that plays quite a big role in terms of reducing that cost. Okay, when we spot this. So when a structure's geometry, loading, material, and boundary conditions have symmetry or anti-symmetry, we can solve a smaller problem. So this is really important to understand. The geometry, the loading, material, and the boundary conditions have to hold for us to be able to exploit symmetry. Okay. And let me just remind you of the scaling typically, that why I say this is a lot faster. Typically if I have a dense matrix and I want to solve a dense matrix, and let's say it's a n by n matrix, a matrix of dimension n, a square matrix of dimension n, then essentially that thing would scale n to the power of 3. If I want to solve twice as much, then it's essentially 8 times longer that I have to wait, because it's going to be, so if it's n, it's n to the power of 3. 2n will be 2n to the power of 3, which is going to be 8n to the power of 3. So it's 8 times longer. That's essentially what we see there. When it comes to sparse matrices, like finite element matrices are really typically sparse. What it means is they have a certain bandwidth. So it's not like a full dense matrix that all the values are non-zero. There's only sort of almost, you can imagine, on the diagonal, around the diagonal, there's a big highway of numbers that are non-zero. The rest far out are typically 0, especially if we've really done effort to make sure that the mesh is properly partitioned. But in those cases, solving a matrix typically scales by n to the bandwidth squared. So that's really what the scale factor there is. The n is a constant when not the constant. So the n is the thing that could change if I change the size, but also the bandwidth might change in size when I have a larger matrix, when I have a larger system that I need to solve. The bandwidth doesn't necessarily stay constant, and in that case, things can scale quite significantly. Okay, so then essentially things can be driven by n to 2n. So that scale that's double as long as what I have to wait if I have twice as larger system. But if the bandwidth, that's the best case scenario, if the bandwidth stayed the same, so I'm safe half the time by employing symmetry when I reduce this system by half, or 4 times the time if I reduce it by 4. But if the bandwidth also changes as a function of the problem size, then there's additional savings. Okay, so that's important to understand. So what is symmetry and what is anti-symmetry? Let's just get this down. I'm going to focus only now on symmetry on this left-hand side. Tomorrow we'll worry about the anti-symmetry. So this left-hand side is symmetry, is essentially when I can identify a symmetry plane. If I flip these two things on top of each other, then all the arrows must point in the same direction and fall on top of each other. So if I fold it around this and I clap the thing closed like a postcard, then essentially you'll see that the two arrows, this one and this one, will point So let's say I take this side and I flip it onto this side, both will point horizontally in this direction and both will point vertically in this direction. So this is how symmetry would look for vertical and horizontal forces that are applied. Okay, so we can see the geometry is symmetric, the boundary conditions is symmetric, the prescribed displacements here are symmetric, the material is symmetric, if it's all uniform, for instance in this case, and the loading is also symmetric. Okay, when I have that, when I have symmetry, I can reduce this to essentially saying, let's replace this here. We can throw half the material away and only model half of the structure and apply rollers. That allows me vertical displacement. And you can also see visually what's going to happen. On this plane, things are not going to move left and right. These two horizontal forces are balancing each other out. They're pushing. So this is not like this node will move left or this node will move right. These two forces are the same. Okay, so obviously the magnitudes has to be the same for this to be a symmetrical problem. These magnitudes have to be the same. That is what is implied. But then this will only move up and down. As I apply vertical load, this will make this move up and down. That's all that will happen there. Okay, that's really what this is about. So if we have a problem where we have essentially this clamped dimensions, load of FF applied, I can say reduce this, and this is the mesh, the mesh that is associated with this full structure. I can say, well, let's just model half of it. Instead of modeling this full thing, let's model half of it, and then we put rollers on that edge there. So that is what it boils down to. Okay. So what I want you to do is open the beam 4 elements Q8 load 1 input file and confirm that the elements are correctly numbered compared to the full mesh. Okay. Beam 2 elements Q8 load 1, confirm that the elements are correctly numbered for the half mesh. These are things that you can do on your own time. This is why I'm going to give you some time to work through this in this class. Open the beam for elements Q8 load 1 and confirm that the forces are correctly applied. Open the beam 2. So this is now with 2 elements only. Q8 load 1 and confirm that the forces are correctly applied. Confirm that the boundary conditions are correctly applied for both meshes. Okay, so this is what I want you to do. You need to be able to go and confirm these things. But if I go and I run this now, and I still have that issue with the matplotlib thing, it's obviously something that's changed. This is essentially the solution I get for the full structure. Clamped, loading applied, beautiful solution. Okay, Bob's your uncle. You can see that stunning. You can see sigma xx, and then essentially sigma xy. So that's it. But we have the full solution. Okay, now I have essentially the 2 element solution. Just take note, this was the 4 element solution. Now I take the 2 element solution and I run this as well. And now you can see for yourself what you see here. Okay, so that's magnification factor of this. Let's just magnify the factor the same, otherwise it's not great to compare. Just want to show you here. So obviously everything's a little bit larger, so this is down the left hand side that we're modeling here. And when you look at that, essentially we are comparing this up to essentially that 1/2 there. Okay. When we start looking at the next and say look at the von Mises stress, and we look at the von Mises stress, we can see essentially the range is 2 to 4 here, the range 2 to 4.4. Everything is numerically equivalent. This is not approximately the same, this is exactly the same numerically. Okay. And you can go and subtract vectors and check it out for yourself. So what I've done is I've pulled out a couple of places. So node 5 for instance, 4 elements displacement at node 5, and then the 2 elements displacement at node 5. Let's just show you what the numbers are. This is the number is 0 there, that's 0 there, that's that value, that's that value, numerically equivalent, no difference. Von Mises, and here they'll be exactly the same. You can see here von Mises for that first one, for the first element, von Mises for the second element, for the second, exactly the same. This is now obviously the third and the fourth element on the other side. Okay. But you can see here beautifully, you can see these values also, everything is symmetric. There's symmetry here involved. Okay, so that's all beautiful. And then we can start saying, let's look at the rows, a little bit more of the displacements and compare them with each other. So displacement of the bottom row of nodes of the full structure and the half row of the full structure, and then we can also look at the difference. And what I want to show you is displacements are there for the full structure's bottom, the half structure's bottom, and the differences are numerically 0. Okay, that's really important to take note of. Okay, the next thing we can consider is this, where we apply now horizontal loads, not just vertical but also horizontal loads. and I want you to be able to model this one on your own steam. So this is, you need to add this load and add this load of G, make it whatever you want, and then you go through the same process. Oh, sorry, I ask you to do it, sorry, 500 force units, and then go through the same process where you extract some of the data and compare and see how they compare. Okay, hopefully this was useful so that you can understand what's going on. And just as an interesting question for yourself is, where we're going to be building up this anti-symmetry, for those of you that can work a little bit ahead, you're welcome to, is we're going to end up here. Say, by using symmetry and anti-symmetry, we can actually model this, not as a full structure, but by exploiting symmetry and anti-symmetry. Okay, it's a non-obvious thing to do, not really that difficult to do, but it just requires you just 1 or 2 minutes to just pause, think about it, and then the answer will pop in. So it's not a difficult thing to do, but I just want to show you the kind of things that you can actually model with symmetry and anti-symmetry that at face value might not look like there's any symmetry that you could exploit, because the loading is clearly not symmetrical here. But if you carefully think about this, and you carefully think about this, and you think about if I could combine them in a way that can look like something like this, the answer is yes, and you could get quite a lot of advantage computationally by modeling essentially this as, instead of one smaller problem, it has 2 smaller problems. So they have sort of given the answer away and a hint, but I want you to think about it and see how you would go about trying to solve this from symmetry and anti-symmetry. So this is where we're heading towards for tomorrow. Thank you.